Hello, in this video we're going to be looking at an integration technique called U-Substitution. Let's start by trying to figure out what the integral of cosine x, cosine 3x, and 3 cosine 3x are. So we're going to do this basically using guess and check. Just if we think, okay, the derivative of what is going to give me cosine x? So I want something that when I take the derivative, I get cosine x. If we take the derivative of sine x, we get cosine x. So the integral for cosine x is sine x plus c. We can check that if we take the derivative of our answer. The derivative of sine x is cosine x, and the derivative of plus c is 0. So we do get back this inside function here that we started with. Number 2, what's the integral of cosine 3x? Well, it's not just the sine of x, because we saw in the last problem that the derivative of sine x is cosine x, not cosine 3x. So what we have here is cosine of stuff. It's not just cosine x, it's the cosine of some other function. This is a composite function, so cosine of stuff. So the derivative of what is going to give me cosine stuff? Well, the derivative of sine stuff gives me cosine stuff times derivative of stuff. So that's going to get me a little bit closer. If I take the derivative of sine 3x, I get cosine 3x times 3. So I'm almost there, but not quite. I'm off by a factor of 3. So what happens if I multiply this by 1/3 and then my constant term plus c? Well, when we take the derivative of that, 1/3 sine 3x plus c, we get 1/3, that's a constant multiple. Then the derivative of sine stuff is cosine stuff times the derivative of the stuff, which is just 3. And then the 3 times 1/3 cancels out. And the derivative of c is 0. So we do get cosine 3x. That's what we needed. So the integral of cosine 3x is 1/3 sine 3x plus c. Now for number 3, we have cosine stuff. We also have the derivative of the stuff. So we're in a better situation with number 3. We've got cosine of stuff and we're multiplying by the derivative of the stuff already. So this is just going to be sine of 3x. If we take the derivative of sine 3x, and we'll put our constant term in there as well, the derivative of sine 3x is cosine 3x times 3, and the derivative of c is 0. So this is what we were trying to get back to when we take the derivative. So the answer here is just sine of 3x plus c. So this is what we're working with in this lesson, trying to integrate composite functions. And we kind of use guess and check here to reason it out, but we're going to see a more systematic way to do this. So what we just saw as an example was that when we differentiate a composite function, we use the chain rule, where we take the derivative of the outside function, in this example f, so f prime of the stuff, f prime of g of x, and we multiply by the derivative of the inside function, or the g of x here. So we multiply by g prime of x. If I want to work backwards from that, if I want to now take this answer right here, this is what the derivative is equal to. If I want to integrate that, so that's what I have right here. If I want to integrate that with respect to x, I should get back to what we started with here, the f of g of x. So if we can split our integrand into 2 parts, where one part is the derivative of the inside of the other part, then we know that what we're really trying to do is undo the chain rule here. So we're going to approach these problems in using a step-by-step process. The first thing we want to do to integrate our composite function is to identify what is the inside function, and we're going to call that u. So we'll write down what u is equal to, and then we're going to find du dx. U is going to be some function of x, so we'll take the derivative, and that's going to be du dx. Our next step will be to rewrite the problem so that it no longer has x's in it. We're going to substitute u in for whatever we set u equal to, and then we're going to also substitute something in for the dx so that our new integral only has the variable u in it, not x. And then our final step will be, once we have our problem rewritten in terms of u, to integrate it like we normally would using a power rule or one of the other integration rules that we know. For example, let's say we're trying to integrate 2x times the cube root of x squared plus 5 with respect to x. We want to identify what is the inside function and then what is the derivative of the inside function. So in this case, the inside function is what's inside the square root. That's what we're going to call our inside function. So I'm going to say u is equal to x squared plus 5. And if u is x squared plus 5, next I'm going to find the derivative of u. U is a function of x. So when I find this derivative, it's the derivative of u with respect to x, du over dx equals, and then since I'm taking the derivative with respect to x, the derivative of x squared is 2x and the derivative of 5 is 0. So now I know that du over dx equals 2x. From here, we're going to rewrite our problem now. We're going to substitute u in for the x squared plus 5. So when I rewrite that, it becomes the integral of 2x times the cube root of u dx. Okay, so that in itself is not going to be enough. We're going to have to keep going further with that. But right now I have 2x times the cube root of u dx. So I still have x's in this problem. I want to substitute all of the x's out and replace them with something in terms of u. So to get rid of the dx, I'm going to come back and use this equation to help me substitute something in. So if we want to solve this for dx, I can multiply both sides by dx and I get du equals 2x dx. Now from here, I can divide both sides by 2x and then I'll know what dx is equal to, so I can make a substitution. But notice that I have what I need already. I have du equals 2x dx, and down here I've got 2x times dx. So this 2x times dx is equal to du. That's what this equation right here tells me, that 2x dx is equal to du. So I can replace the 2x dx with du. And if I do that, I replace the 2x dx with du, then what I'm left with is the cube root of u times du. And this is what I want. I want an integral that no longer has x's in it. I just want my new variable to be a u. So here I'm good to go. I can move on to step 3, which is where I actually do the integration. And the cube root of u, if I want to use my power rule, it's easier to think of that as u raised to the power 1/3. And then we use our power rule for integration where we add 1 to the power, so I get u to the 4/3, and then I divide by the new power. Dividing by 4/3 is the same as multiplying by 3/4. And then since this is an indefinite integral, I'm going to put plus c at the end as a placeholder for a constant term. Now you might think, okay, great, we're done. We've integrated this. But we've actually integrated it with respect to u, and the original problem asked us to integrate with respect to x. So what we want to do at the very end is rewrite the problem back in terms of x, and we can just do a reverse substitution. We know that u equals x squared plus 5, so we're going to replace the u with x squared plus 5. So I get, instead of 3/4 times u to the 4/3, I get 3/4 times x squared plus 5 to the 4/3 plus c, and that will be my final answer. In our next example, we want to integrate 2x over x squared plus 3. So I'm looking at this and I have to decide what am I going to consider my inside function? Well, keep in mind that once we choose our inside function u, we have to take the derivative of it. And so if I let 2x be my u, the derivative of that is just 2, and then somehow I'm still going to have to get rid of the x squared plus 3. So that doesn't seem promising. However, if I set my denominator equal to u, If we say u equals x squared plus 3, then the derivative of that is 2x, which is what I have on the top. So that's going to be helpful. We're going to let u equal x squared plus 3. And it is often the case when you have a fraction that you're going to choose the denominator to be your u. So now we have u equals x squared plus 3. We're going to find du dx. Du dx equals, I'm just taking the derivative of x squared and then taking the derivative of 3. So I have du over dx equals 2x. So I have what I need to start making substitutions. I can substitute x squared plus 3 for u. So that's going to give me the integral of 2x over u dx. Now I still have to get rid of the dx. So I can, as one option, solve this equation here for dx. So to do that, I might, as a first step, multiply both sides by dx. And if I do that, I get du equals 2x dx. From here, if I want to solve for dx, I can divide both sides by 2x. But again, notice what this says. It says that du equals 2x dx, and I have 2x dx right here in my integral. So 2x dx is equal to du. I can just make a substitution right now. That's equal to du over u. I prefer to separate the du and write it at the end, so I prefer to see this as 1 over u du, but you can write it either way. So now I have accomplished my goal for step 2, which is to rewrite the problem only in terms of u. I no longer have x's in my problem. My new variable here is just a u. So I'm ready to go ahead and integrate this. What is the antiderivative of 1 over u? It's the natural log of the absolute value of u plus c. And then for my final answer, I want the problem in terms of my original variable x. So I'm going to replace u with x squared plus 3. So we have ln absolute value x squared plus 3 plus c. Now we need the absolute value around the u when we integrate 1 over u. However, now that I've substituted x squared plus 3 back in for u, I can see that this is always positive. X squared is either 0 or it's positive, and then when we add 3, we get something that's positive. So it would be okay in this problem to drop the absolute value and just say it's the natural log of x squared plus 3 plus c. Or you could leave the absolute value in there. The absolute value does not make it wrong. So ln of x squared plus 3 plus c. Our next example, we want to integrate x over the square root of x squared plus 3. So again, we have to think about, what am I going to choose for my inside function? Should I let u equal x? Should I let u equal the square root of x squared plus 3? Should I let u equal x squared plus 3? Should I let u equal x squared? So we're going to try, remember, the goal is to get rid of all of the x's. If I let u equal x squared plus 3, then the derivative of that is going to be 2x. And that's going to help me get rid of the x on the top. So we're going to let u equal x squared plus 3. And sometimes this is going to be guess and check. You might pick the wrong thing for u. And if you do, you're probably going to get stuck when you try and get rid of all of your x's. So if that happens to you, don't get frustrated. Just go back and try and choose something else for u and see if that makes the problem easier. So now that I've chosen my u, I'm going to take the derivative with respect to x. So du dx equals 2x, and the derivative of 3 is 0. So now I want to try and start making substitutions. I know that u equals x squared plus 3, so I can rewrite this as the integral of x over the square root of u dx. So I'm not done with my substitution yet. I still have to get rid of the x in the numerator and the dx. So I'm going to come back over to my derivative equation, and I'm going to multiply both sides by dx. So that's going to give me du equals 2x dx. Now, one option, some people like to do it this way, is to solve this equation for dx. So by that I mean you can divide both sides by 2x. and then you'll know what dx is equal to, and you can substitute that over here for the dx. I tend to find that's a little extra work to do it that way, so I try and match instead. I can see here that I have an x dx that I need to get rid of. I need to get rid of x dx. So in this equation, I would like to isolate the x dx, and to do that, I'm going to divide both sides by 2, which is the same as multiplying both sides by 1/2. So 1/2 du equals x dx. And now that I know what x dx is, it's 1/2 du, I can substitute that for the x dx I have in my integral. So now I have the integral of 1/2 du over the square root of u. And that doesn't look that great. I'm going to rewrite this a little bit. I like to write the du at the end. It's just multiplied, so it's okay if we bring it out of the fraction and just multiply it at the end. And then 1/2 over the square root of u is the same as 1 over 2 square root u. Okay, so that looks a little more standardish form. I've gotten rid of my x's. My new variable is only a u, so I'm ready to integrate this. And this is one of the rules that I have memorized. This is the derivative of the square root of u. So I know the antiderivative of 1 over 2 root u is just square root of u plus c, because this is an indefinite integral. And so for our final answer, we're not going to leave u in our final answer. We're going to go back to what u is equal to, x squared plus 3, and substitute that in for the u. So x squared plus 3, square root of x squared plus 3 plus c will be my final answer. Next, we have the integral of e to the cosine x sine x dx. So we need to choose our u. Again, we've got options. Should u equal e to the cosine x? Should u equal sine x? Should u equal cosine x? So when you're trying to run through the possibilities, think, okay, whatever I let u equal, I'm going to have to take the derivative of it, and I want the derivative to be present so I can make a substitution. So if I let u equal cosine x, the derivative of cosine x is negative sine x. So we have a sine x here that we don't have negative sine x, we have positive sine x, but that's okay. When you're off by a constant multiple, that's very easy to adjust. So I'm not worried about that. Or what if I let u equal sine x? The derivative of sine x is cosine x, and I have a cosine x in here. However, let's just play through that scenario for a moment. What if I let u equal sine x? If I let u equal sine x, then this right here becomes a u. And the derivative of sine x is cosine x, so this is going to become a du, and then it's going to be really weird. It's going to be the integral of e to the power du times u, and then this dx is going to kind of become a part of the cosine x dx will be my du. So that's not going to work. We can't have a du in an exponent. That doesn't even make sense. Remember, with our integral is just a special Riemann sum, and the du is the width of our interval. When we're doing a Riemann sum, it's the width of the rectangle. So we don't want that in an exponent. We always want to be multiplying by du at the end. So we're not going to choose sine x for our u. Let's do cosine x for our u and see what happens there. If I let u equal cosine x, then du dx equals negative sine x dx, just negative sine x. Now I'm going to start making my substitution. So I have the integral of e to the power u. Since u equals cosine x, e to the cosine x becomes e to the u. Then I'm still left with this sine x dx here. So I have e to the u times sine x dx. Let's go back to our derivative equation. If I multiply both sides by dx, then I get du equals negative sine x dx. So again, if you like, you can solve this equation for dx by multiplying both sides by negative sine x. I prefer to try and get a match with whatever I have left over in my integral. I'm trying to get sine x dx. So I'm going to solve this for sine x dx. And to do that, I just multiply both sides by -1 or divide both sides by -1, however you prefer to think about that. So negative du equals sine x dx. And now I can make that substitution. Negative sine x dx becomes negative du. So I get the integral of e to the u times -1 times du. And multiplying by -1, when you multiply by a constant, we've seen the property where you can bring the constant outside of your integral. So we just multiply the whole integral by -1. And this is a really simple antiderivative. The antiderivative of e to the u is e to the u. We've got this constant multiple in front, so negative e to the u plus c. And my final answer, I'm not going to leave the u, I'm going to substitute something back in for u, so negative e to the cosine x plus c. And I didn't mention this earlier, but remember when you're integrating, you can always check your answer by taking the derivative of your answer. To take the derivative of negative e to the cosine x plus c, we would have to use chain rule. It's not that bad. Next example. So by now you should be pausing and trying these on your own first, and then you can watch me work through it if you need the extra guidance. So we have to choose, what is our u going to be? Is it going to be x? Is it going to be 2x minus 1? Is it going to be 2x minus 1 cubed? Remember that our u is our inside function. So what seems the most natural choice for an inside function here? Let's try the 2x minus 1. What is inside the parentheses? If I let u equal 2x minus 1, then du dx, the derivative of u with respect to x, is just 2. Let's try and rewrite our integral. So I have x times u cubed dx. Okay, so we have this x dx that we still need to get rid of, x dx. And if I go to my derivative equation, I can multiply both sides by dx, and that gives me du equals 2 dx. Well, that doesn't match what I still have left over. I don't have a 2 dx. I have an x dx. So somehow I have to get rid of this x right here. The 2, not really a problem. That's just a constant multiple. I can divide both sides of this equation by 2, and I have 1/2 du equals dx. But I don't have an extra x in this equation. So let's just use what we have. We can replace dx with 1/2 du and see where that leaves us. So this is going to be the integral. I've still got that x there, u cubed, but then the dx is going to get replaced with 1/2 times du. The 1/2 is a constant multiple. I'll bring that out front, du. So I'm almost ready to integrate, but not quite, because I still have this extra x hanging out over here. So what does x equal in terms of u? If I knew what it was equal to in terms of u, I could make another substitution. Well, I don't have it written down yet, but I can figure this out because u equals 2x minus 1. And if u equals 2x minus 1, I can add 1 to both sides and get u plus 1 equals 2x. And then I can divide both sides by 2 and get u plus 1 over 2 equals x. And now I know what x is equal to in terms of u, so I can make a substitution. So let's rewrite what we have, 1/2 times the integral, and instead of x, now I'm going to put u plus 1 over 2. Times u cubed, that's still there, and then times du. So now I have an integral that only has u's in it. I've gotten rid of my x's, so I've accomplished my goal for step 2, and I'm ready to try and integrate. But I'm not really ready to integrate because this is now a product, and we don't have a product rule for integration, so I need to simplify this as much as possible. So I'm noticing I have u plus 1 over 2. That's the same as u plus 1 times 1/2. So that Let me just write it out. 1/2 times u plus 1 times u cubed times du. So this 1/2 I can bring out as well, and it gets multiplied by the 1/2 that's already out there. So it becomes 1/4 integral u plus 1 times u cubed. I'm going to distribute that u cubed. So I get u to the 4th plus u cubed times du. And now I'm ready to integrate using my power rule. So this is equal to 1/4 times, so using our power rule, u to the 4th becomes u to the 5th over 5, plus, and then u cubed becomes u to the 4th over 4, plus c. And for our final answer, we don't want to leave the u in there. We want to sub 2x minus 1 back in for u. So 1/4 times 2x minus 1 to the power 5 over 5 plus 2x minus 1 to the power 4 over 4 plus c. Our next example, we want to integrate 2x plus 1 over the square root of x plus 4. So what are we going to choose for our u? We could let u equal 2x plus 1. We could let u equal x plus 4. We could let u equal the square root of x plus 4. Keep in mind u is our inside function, so just kind of what naturally seems like it's inside of something, I'm going to go with x plus 4. It's inside of the square root, which is inside of the denominator. So we'll try it. If it doesn't work out, we can start over with a different choice of u. So I've got u equals x plus 4. Now when I take my derivative, du dx equals, well, the derivative of x is just 1 and the derivative of 4 is 0. So let's go ahead and multiply both sides by dx. Now this is a simple case where we have du equals dx. So now this means I'm allowed to replace dx with du because they're equal to each other. So that should be helpful. Let's rewrite our integral. On the top I have 2x plus 1. On the bottom I have the square root of x plus 4, which now is the square root of u. And then times dx, but dx is equal to du. So I just have this one little problem right here that I have to get rid of. I don't want an x there. So I'm going to go back and use my equation for u, and instead of writing u in terms of x, I'm going to solve this for x in terms of u. And this one is pretty simple to solve for x. We just subtract 4 on both sides, and we get x equals u minus 4. Okay, so now I know that u is x plus 4, and x is u minus 4. So instead of 2x, I have 2 times u minus 4 plus 1 over the square root of u du. So that looks kind of complicated. We can't integrate right now because it's in the form of a quotient and we don't have a quotient rule for integrating. So we need to simplify this as much as possible. Let's distribute the 2 on the top, add 1, combine like terms. So we get 2u and then minus 8 plus 1, so 2u minus 7 over the square root of u times du. And we'll continue to simplify this. I'm going to do 2u divided by root 2 and then minus 7 divided by root u. So 2u divided by root u is 2 root u minus 7 over root u times du. And I'm going to rewrite these with fractional exponents so that I can use my power rule more easily. So this is 2u to the power 1/2 minus 7u to the power negative 1/2 times du. Let's use our power rule where we add 1 to the exponent. So 2u to the 3/2 divided by 3/2 is the same as multiplying by 2/3 minus 7u negative 1/2 plus 1 is a positive 1/2. And then I have to divide by 1/2, which is the same as multiplying by 2 plus c. So that's 4/3 u to the 3/2, and u is x plus 4, minus 14 u to the 1/2, so x plus 4 to the 1/2 plus c. If you like, you can go back to radical notation, but I would probably just leave my answer in this form here. For our next example, we have a definite integral. So we're going to start this the same way we started the other ones. When it was an indefinite integral, we have to figure out what are we going to choose for u, and then we're going to take the derivative and make our substitutions. So I'm going to let u be what's inside the square root. U equals 2x plus 1. And then I have my derivative, du dx equals 2. Now when you have a definite integral and you're multiplying by dx, the width of your interval is the change in x. And that means that these bounds right here, this lower bound and this upper bound, those are x values. So we have to be careful with our notation. When we change variables, we're also going to have to change our bounds, because the 0 at the top, that's an x value. That's not a u value. So I can either figure out what is u when x is 0, and I have an equation that will help me do that right here. When x is 0, u is 2 times 0 plus 1, or 1. So I can say at x equals 0, u is equal to 1. And for my lower bound, at x equals negative 1/2, u equals 2 times negative 1/2 plus 1. 2 times negative 1/2 is negative 1, plus 1 is 0. So when I rewrite my integral in terms of u, I can change the bounds to go from 0 to 1. All right, let's see what else we have in terms of our substitution, because we've got this extra x out here that I think we have to deal with. So I've got the integral of x times the square root of u, and then I need to replace my dx. So what is dx? Well, if I multiply both sides of my derivative equation here by dx and I divide both sides by 2, I get 1/2 du equals dx. So I'm going to replace the dx with 1/2 du. Bring the 1/2 out front and then du. So I do have to get rid of this extra x, and to do that, I'm going to come back to my u equation and solve it for x. So if u equals 2x plus 1, then I'm going to subtract 1 on both sides to get u minus 1, and then divide by 2 on both sides, and that will give me x. So now my integral becomes 1/2. X gets replaced with u minus 1 over 2 times square root of u du. And I haven't put any numbers here and here yet, but I can at this point do that because I've rewritten my problem entirely in terms of u. So I can use my new u values. I said when x was negative 1/2, u was 0. So I can put a 0 there. And then when x was 0, u was 1. So I can change that to a 1 right there. That's one option. You also have the option of just leaving it blank. Just leave those bounds blank. And when we get to the very end, so pretend it's an indefinite integral. And when you get to the very end, when you substitute the x's back in for the u's, then you can use those original bounds and evaluate it. So I don't know that one way is any easier than the other. I think it's usually the same amount of work either way. But since I started this one this way, let's carry it through. So now I have to do some simplifying before I integrate. So this dividing by 2 right here is the same as multiplying by 1/2, which I'm going to bring outside of my integral. So I get 1/4 integral from 0 to 1. And then I want to distribute this square root of u. So I have u times the square root of u minus the square root of u. All of that times du. And let's rewrite using fractional exponents to make it easier to do our power rule. So u times square root of u is u to the power 3 over 2 minus u to the power 1/2, and that gets multiplied by du. So I'm ready to integrate. Step 3, 1/4, and then the antiderivative of u to the 3/2, I'm going to add 1 to that, so I get u to the 5/2 divided by 5/2, which is the same as times 2/5, minus u to the 3/2 divided by 3/2, or times 2/3, and this is a definite integral, so I don't need the plus c, but I do need to evaluate from 0 to 1. Remember, these are my u values. So I substitute in my upper bound, 1 for u, and I get 1/4 times 2/5 minus 2/3, minus, and then I'm going to substitute in the lower bound, 1/4 times 0 minus 0. So that all just is 0. And I just need to simplify now the 1/4 times 2/5 minus 2/3. So that's 1/4 times, I'll use a common denominator of 15. So to get 15 from 5, I multiply by 3. 2 times 3 is 6. To get 15 from 3, I multiply by 5, and 2 times 5 is 10. So now I have -4 on the top, which will cancel with the 4 on the bottom and just leave a -1 behind. So final answer, -1 over 15. Okay, now it's time for you to practice. So you should pause the video and try these 6 practice problems on your own. I'm going to work through them rather quickly here. Number one, I'm going to let u equal 2x plus 3. Then du equals 2 dx. So my integral becomes the sine of u, and the 2 dx becomes du. The integral of sine is negative cosine. So I have negative cosine u plus c, and then for my final answer, I substitute 2x plus 3 back in for the u. So negative cosine of 2x plus 3 plus c. Number 2, my u is x squared plus 2x. My du over dx is 2x plus 2. So I get du equals 2x plus 2 dx, and then my integral becomes 1 over u times du. And when we integrate 1 over u, we get natural log absolute value u plus c. So ln absolute value x squared plus 2x, we cannot drop the absolute value here because x squared plus 2x could be negative if we drop the absolute value, and we don't want to allow for that. Number 3, we're going to let u equal 3x plus 2. So du equals 3 dx. And when I rewrite, I get cosine u 1/3 du. So I'm missing the 3 on that one. I have here cosine of u, and then I only have a dx left over. I don't have the 3. So to compensate for that, it's like I'm multiplying by 3 to put it in there, but then to compensate, I have to multiply by 1/3 on the outside. So that's the way I reason through that one. Your other alternative would be, okay, if you saw, okay, du equals 3 dx, you can solve this for dx, and you get 1/3 du equals dx, and then you replace your dx with 1/3 du. Okay, then the integral of cosine u is just sine u, so I have 1/3 sine u plus c, or 1/3 sine of 3x plus 2 plus c. Number 4, u equals 3x, then my du equals 3 dx. So I have the integral of 5 e to the u and then 1/3 du. And the 5 can come out with the 1/3. So 5/3 times the integral e to the u du equals 5/3. The antiderivative of e to the u is e to the u plus c. So 5/3 e to the 3x plus c. And number 6, we're going to let u equal 2x squared plus 3. Then du equals 4x dx. My integral becomes, so I've got 3x dx here, 3x dx. Ideally, I'd like to have a 4x dx. So I'm going to go ahead and put a 4 here, and then I have to put a 1/4 out front to balance that. And I have to bring the 3 out. So I end up with 3/4 on the outside. The x dx becomes du, and I have 1 over square root of u. Now I'd rather have 1 over 2 square root of u because I know the antiderivative of that. So if I split this 4 into 2 times 2, I can leave 1 2 outside and bring one of the 2's inside. And then I have 3 over 2 times the square root of u plus c. Or 3 over 2 times the square root of 2x squared plus 3 plus c.